Hello everyone. In this particular video lecture, I would like to elaborate the steps which can be taken up in order to compute the number of turns which is required on the interpole windings of a DC machine. I mean to say, on what basis or on what approach we can calculate the number of turns which has to be placed on the interpole. So before I start upon, or before I embark about the procedure for calculating the number of turns of interpoles, allow me to just recapitulate certain things so that we don't have to refer somewhere else for any kind of conceptual clarification. So let me just review some things. What is shown here is your cross-sectional view of a two-pole DC machine. So I have indicated a cross-sectional view of a two-pole DC machine. Again, I would say the same thing, that why I have taken up number of poles to be 2, because if we take number of poles to be 2, in that case there is no confusion or ambiguity between electrical degree and mechanical degree, because we know that theta electrical is given by P divided by 2 and this whole thing multiplied by theta mechanical. So if the number of poles is taken as 2, then theta electrical degree and theta mechanical degree are same. So you don't have to bother about the electrical degree and mechanical degree. Mechanical degree is something which we can see with our bare eyes. So whatever we see with our bare eyes, that is the mechanical degree. And if you multiply the mechanical degree by P by 2, in that case you will obtain the electrical degree. Here P is in this case the P is indicating the number of poles. So now what you can see here in the diagram is that this cross-sectional view is being taken along a plane, the plane being normal or perpendicular to the shaft of the DC machine. That means we have imagined that the DC machine is being cut by an imaginary plane, and the plane being normal or perpendicular to the shaft of the DC machine. So that's why you are seeing a circular structure at the center. Actually, this circular structure stands for the armature core of the DC machine. As we are aware that the geometric shape of the armature core of a DC machine is cylindrical in nature. Actually, to be precise, the armature core of a DC machine is a laminated cylindrical structure so as to minimize the eddy current loss. And these are your field poles. This is the pole face, this is the pole body, these are the field winding or field coils, and you can see there is a armature slot shown on the armature core. So in this particular diagram I have indicated 12 number of armature slots. Obviously, if there are 12 number of armature slots, then the number of armature teeth will be also 12. Now what is I have indicated in the armature core is a single layer winding. Single layer winding means a particular slot on the armature core is going to accommodate or house only one coil side. On the other hand, if double layer winding is being used, in that case in a particular slot you will have two coil sides of two different coils. Obviously, whatever analysis we are going to make out for this single layer winding, the same will be also applicable for double layer winding. Just for making sure that the diagram is not getting much clumsier, I have taken single layer winding, but let me tell you that in actual practice or in reality you will find that in most of the DC machine the type of winding which is employed in the armature core is actually double layer winding. Single layer winding is hardly used. Single layer winding is not used. Actually, for DC machine, the armature core is invariably fitted with a armature winding, which is happens to be double layer winding. Okay, now let us make some assumption. I mean to say that a DC machine can operate either as a generator or it can operate as a motor. So we have to take some mode of operation so that we can further our analysis. So I am assuming that the DC machine is operating as a generator. So I am assuming generating mode. So if it is generating mode, in that case there has to be a prime mover, and that prime mover will drive the armature core of the DC machine. So the function of the prime mover in case the DC machine is operating as a generator is that it provides the mechanical energy as input. So what is done, the shaft of the prime mover, you can take the prime mover to be a diesel engine for example. So what is done, the shaft of the prime mover and the shaft of the armature core of this DC machine, they are mechanically coupled. So the armature core is able to share the motion which is being imparted by your prime mover. So I am assuming that prime mover is driving the armature core in clockwise direction at a uniform angular speed of omega r mechanical radians per second. Now I have indicated 12 slots in the armature core, and I have assumed that the armature core is having armature winding which is of single layer type. So I am assuming single layer winding. So if it is single layer winding, and you know that a coil has got two sides, so obviously 12 number of slots on the armature core, 12 number of slots on the armature core can accommodate 6 number of coils, since we have assumed single layer winding. Had it been double layer winding, in that case the armature core would have been able to accommodate 12 number of coils with 12 number of slots present in case of double layer winding. But for single layer winding, it will accommodate 6 coils because it is having 12 number of slots in the armature core and a particular coil has got two sides. So you can just see for yourself that the first coil is having its coil sides placed in slot number 1 and 1 dash. Likewise, the second coil is having its coil side placed in slot number 2 and 2 dash. Like that, you have placed 6 coils. So what you can notice is that any particular coil is having its coil sides placed in the armature slots which are diametrically opposite, isn't it? You see here, if you take a coil which is placed in slot number 1 and slot number 1 dash, so these two slots named as slot number 1 and slot number 1 dash, these two slots are diametrically opposite. Means what? That the mechanical degree between this slot number 1 and 1 dash, the mechanical degree, that is theta mechanical, between slot number 1 and 1 dash happens to be 180 degree, and it has to be because in the beginning itself we have assumed that we will take up a case of 2-pole DC machine. So if the number of poles on the stator is 2, if the number of poles developed on the stator is 2, in that scenario you will expect that the number of poles developed in the armature core of DC machine, it has to be also 2, because for development of electromagnetic torque, what is needed? For development of electromagnetic torque, it is needed that number of poles developed on the stator and number of poles developed on the rotor, they should be equal. Then only electromagnetic torque can be developed. So in order to make sure that only 2 poles are developed in the armature core, what is done? When we are placing the armature coils in the armature core, the armature coils are placed in such a way that they are satisfying the relation theta electrical equals P by 2 theta mechanical. Since here we have taken P as 2, so 2 and 2 gets cancelled, so we get theta electrical equals to theta mechanical, and we are going to place full pitch coil. Full pitch coil means what? Coil span is 180 degree electrical, so we get that theta mechanical should be 180 degree electrical also. So since theta mechanical is coming as 180 degree electrical, as per that calculation, that theta electrical equals to P by 2 theta mechanical. Here P is 2 and we are considering full pitch coil, so theta electrical will be 180 degree. So from that relation we are finding that theta mechanical is coming as your 180 degree. So since theta mechanical is 180 degree, the coil sides of a particular coil, the coil sides of a particular coil has to be placed diametrically opposite like this, like 1 1 dash, 2 2 dash, so and so on. Now what should I say is that in this armature core I have indicated 6 coils named as 1 1 dash, 2 2 dash, 3 3 dash and so on. But you see there is another coil shown by this green color. So this coil shown by green color is indicated as coil CC dash. So actually this coil CC dash, it is not any particular coil. What I mean to say is that we have assumed that there are 6 coils placed on the armature core. So again I am going to stick to that. Again I will reiterate that there are 6 coils placed on the armature core. It is not like that this coil CC dash will get counted and it will become 7 coils. No, actually this coil CC dash is indicating, this coil CC dash is indicating the position which is occupied by the coil which is undergoing commutation. So here the coil CC dash is shown, or the coil CC dash is drawn just to indicate that this is the position of the coil which is undergoing commutation. So simply speaking, you can say CC dash is indicating the position of the commutated coil. Now out of these 6 coils, which coils has to be taken as commutated coil? Please focus on the diagram. You see this coil which is placed in slot number 1 and 1 dash, this coil which is placed in slot number 1 and 1 dash, it is very near to the brush. So what happens? The armature core is being driven by the prime mover in clockwise direction. What happens when this coil whose sides are placed in slot number 1 and 1 dash will come to the position indicated by coil CC dash? What will happen? Coil 1 1 dash will be then termed as the commutated coil. So whichever coil is going to occupy, whichever coil, it can be 1 1 dash, it can be 2 2 dash, it can be 3 3 dash, whichever coil is going to occupy the position which is indicated by the coil CC dash, so that coil will be said to be undergoing commutation. That means what? After few degrees of rotation, you can look at the diagram. As per this diagram, you will find that after few degrees of rotation, this coil side 1 1 dash will come to the position which is now occupied by coil CC dash. Am I clear? After few degrees of rotation, what will happen? In the clockwise direction, of course, because the armature is rotating in the clockwise direction, or rather I would say the prime mover is driving the armature core in clockwise direction. So after few degrees of rotation, what will happen? Coil 1 1 dash will come to the position which is occupied by coil CC dash. So at that moment we will call that coil 1 1 dash is undergoing commutation. After another few degrees of rotation, what you will expect? Coil 2 2 dash will occupy the position of CC dash. So in that way, what will happen? Each of the 6 coils which are placed on the armature core are going to get commutated. Each of the 6 coils. That means coil 11 dash, coil 22 dash, coil 33 dash, and so on. Each of the 6 coils is going to get commutated at some point of time, or you can say that each of the 6 coils is going to occupy the position which is indicated by coil CC dash. Okay, so just coil CC dash is some sort of reference. It is indicating the position of the coil which is undergoing commutation. Now, what is a commutation actually means? What is the meaning of commutation? Commutation means the reversal of armature coil current. So, what is the meaning of reversal? You please look at the diagram. At this particular moment, if we focus on coil 11 dash only, so coil side 1 is having a induced EMF polarity which is cross, and coil side 1 dash is having a induced EMF polarity which is shown by dot. But after few degrees of rotation, what is going to happen? The coil side 1 will occupy, or rather coil side 1 will come to the position which is at present occupied by coil side 6 dash, and at the same time what will happen? Coil side 1 dash will occupy a position which is presently occupied by coil side 6. So allow me to tell me once more if you have missed in case. What I am saying, that after few degrees of rotation, what is going to happen? Coil side 1 will occupy a position which is presently occupied by coil side 6 dash, and simultaneously coil side 1 dash will occupy a position which is presently occupied by coil side 6. So what will happen? The induced EMF polarity of coil side 1 will change from cross to dot when coil side 1 moves to this position which is occupied by coil side 6 dash, and at the same time the induced EMF polarity of coil side 1 dash will change from dot to cross the moment coil side 1 dash is occupying the position which is occupied by coil side 6 at this moment. So what you see, that once the coil is traversing the width of the brush, the induced EMF polarity on the coil side is getting changed. You can just look here only in the diagram, that after few degrees of rotation, what will happen? After few degrees of rotation, what will happen? Coil side 1 will occupy a position which is presently occupied by coil side 6 dash. That means it will become from cross to dot, and at the same time, or rather simultaneously, it will happen also that coil side 1 dash will occupy a position which is presently occupied by coil side 6. So hence it will become from dot to cross. So for this particular coil 11 dash, what do you see? That when it moves from the position 11 dash to the position 66 dash after few degrees of rotation, the induced EMF polarity in coil side 1 and 1 dash is getting changed from cross to dot and dot to cross. So there is a reversal of coil current carried by the coil 11 dash. When it is getting reversed, the moment it is switching from this side, that is occupied by position 11 dash, to this side, that is occupied by position 6 dash. Okay, so here it is occupying position 11 dash. The moment it moves to this side of the brush, this is 11 dash. So the moment the coil 11 dash moves to this side of the brush, it will occupy a position which is presently occupied by coil side 6 dash 6. So what will happen? Cross will turn into dot and dot will turn into cross. So there is a reversal of coil current. Now how much time is needed for this reversal of coil current? The time needed for this reversal of coil current is the time which is needed to traverse the width of the brush. So if this is the width of the brush, so whatever time is needed to traverse the width of the brush, that is the time in which the coil current has to become from cross to dot and from dot to cross. So this time during which the brush width is being traversed is known as commutation time TC. So it is indicated by TC. Now the commutation time TC is nothing but it is given by TC is given by brush width, let's say WB. Let's say WB is the brush width and say V is the peripheral velocity of the commutator. So brush width, that is distance, divided by speed is what? Time. So commutation time TC is nothing but W by Vc. What is Vc? Vc is the peripheral speed of the commutator and WB is the width of the brush. So TC equals to W by Vc. So in this much time only, what should happen? The coil current direction in coil 11 dash should change from cross dot to dot cross, because coil side 11 dash will occupy from this position to this position, which is now occupied by 6 dash and 6. So it will change from cross dot to dot cross. So you see, this was the coil current carried by coil 11 dash. This was the coil current carried by coil 11 dash just before coming in contact with the brush, and this is the current carried by the coil 11 dash, that is minus Ia by A, when it is leaving the brush contact. So this is the time instant. This is the time instant at which the coil 11 dash is coming in contact with the brush, and this is the time instant at which the coil 11 dash is leaving the brush contact. So it has changed from plus Ia by A to minus Ia by A. Now just for ease of understanding, I have tried to represent here a small figure. You see here, these red lines are nothing but they are mica insulation, and these are the commutator segments. So between any two commutator segments, you will find that there is a mica insulation of around thickness which is 0.8 mm. Now this is the brush. So now what happens? You see, you may call this to be your, let's say, segment number. Let's say this is segment number 1 and this is segment number 2. So what do you see? That the two ends of the coil CC dash are connected to commutator segment 1 and commutator segment 2. So now what happens? The moment commutator segment 1 and 2 comes in contact with the brush, what happens? The coil CC dash gets short circuited. And what is the path of the short circuit current flow? You see, this red line between commutator segment 1 and 2. This red line between commutator segment 1 and 2 indicates the mica insulation. So current cannot pass from commutator segment 1 to 2. However, when the brush is in contact with a portion of commutator segment 1 and a portion of commutator segment 2, what you can expect, that current will take up this path which is indicated by this blue line. You see, you follow this blue line. So from I am moving along the coil sides, then I am entering to commutator segment 2, I am entering the brush, I am entering commutator segment 1, again I am passing through this coil side. So you see, this particular blue line will let you know the path which can be taken up by the commutated coil CC dash when this commutated coil CC dash is getting short circuited by the brush. How it is getting short circuited, you can view easily that the two ends of the coil CC dash are in contact with commutator segment 1 and 2, and the moment commutator segment 1 and 2 are coming in contact with the brush, then this coil CC dash gets short circuited and the path of the short circuit current flow is indicated by this blue line. Okay, now what will happen? This is the commutator segment. So commutator segment is rotating. So however, the brush is stationary. So this is the brush is stationary, it will not move, but commutator segment will move. So after some time, what will happen? The brush will break the contact from segment 2 and it will have contact fully on segment 1. In that case, you will say that the commutation of coil CC dash has been completed, because now the coil CC dash is no longer in contact with the segment 1 and 2. Rather, sorry, what should I say? That the moment what happens, the brush is stationary and the commutator segment is moving. So what will happen? A time will come when the entire brush is on segment 1, is on commutator segment 1. So in that case, what will happen? The two ends of the coil CC dash will not be getting short circuited anymore, because now what happens, the entire portion of the brush is in contact with segment 1. Earlier what was happening, that brush was in contact with both segment 1 and segment 2. A portion of segment 1 was in contact with brush, a portion of segment 2 was also in contact with the brush. So this position where the brush is in contact with both segment 1 and 2 simultaneously will lead to short circuiting of the coil CC dash. But when the brush is fully on segment 1, when the brush is fully on commutator segment 1, at that point the coil side CC dash is no longer going to be get short circuited. It won't be short circuited at that point of time when the brush is fully on segment 1 or say segment 2. Now, so what I was saying is that this is the time instant at which what is happening, the brush is in coming contact with the segment 1. It was earlier in contact with segment 2 fully, but at this moment the brush is in coming contact with both segment 1 and 2. So here the coil gets short circuited and the coil current starts to reverse, and at this point the contact with the segment 2 brush, at this point the contact with the commutator segment 2 is broken and the brush is fully on commutator segment 1. So here the contact is broken and the commutation is completed. Now, why the coil current IC is written as IA by A? This is because if you take IA as the armature current and small a as the number of parallel path in the armature circuit, then since there are a number of parallel path in the armature circuit and IA is the current which is entering the brush, so this current IA which is entering the brush is going to get distributed equally in those a number of parallel path. So the current in each parallel path will be IA by A. Of course, in each parallel path you will have some armature coils connected in series. So in each parallel path you are having some armature coils which will be connected in series. So obviously the current carried by each armature coil will be equals to IA by A. So that's why IC is nothing but IC is the current carried by a particular coil. What is IC? IC is the current carried by a particular coil, and it is given as IA by A because IA by A is the current carried by each coil or each conductor, as IA by A stands for the current through each parallel path. Now, what needs to be quickly revised by this diagram is that you can figure out the cross and dot for field coils, cross and dot for field coils. So this cross and dot for field coils will give you this to be north pole and this to be south pole. You can apply that right hand rule. Cross means what? Current is entering the board. So my 4 fingers of the right hand will enter inside the board and it will come out from this side. So thumb is giving you the magnetic lines of flux direction. So from this pole phase magnetic lines of flux are leaving, from this pole phase magnetic lines of flux are leaving. So this is north pole, and on this pole phase you will find that magnetic lines of flux are entering. So this will be our south pole. So this is your north and south pole which is drawn here separately. So what is BF here? BF is representing the magnetic, BF is representing the magnetic flux density vector due to field coil current, okay. Now what about this BCP? What is BCP? BCP is the magnetic flux density vector due to the current carried by the interpole windings. The interpole windings are placed along the interpolar region. These interpoles are also known as com poles, or they are also known as commutating poles, and they are fitted along the interpolar region. So what is an interpole? An interpole is a narrow pole, and interpole is a narrow pole which is fitted along the interpolar axis. Interpolar axis is that axis along which air gap is maximum. So interpoles are narrow poles which are fitted to the yoke, along the interpolar axis. So this is the interpoles fitted to the yoke along the interpolar axis. Along the interpolar axis, air gap is maximum. So you can find by that right hand grip rule. Cross means what? Current is entering the board, dot means leaving. You see thumb is pointing outwards. So the magnetic lines of flux due to these interpoles is directed in upward directions, as you can find from the right hand grip rule. Cross means entering, dot means leaving. So thumb is upward. Now these are the two magnetic lines of flux direction. This is for field coil and this is for interpole. So this is for main field pole. You can also call this to be the flux density. BF is also can be called as the flux density due to main field poles, and this is the flux density due to interpoles or commutating poles or com poles. Now what about the magnetic axis of the armature? Now you see there are different ways of finding the magnetic axis of armature winding. One way is very simple, as I have said in the beginning, that there are 6 coils in the armature core. Now these 6 coils in the armature cores, they are distributed throughout the armature core periphery. You can see for yourself that these 6 coils named as 1 1 dash, 2 2 dash, 3 3 dash, these 6 armature coils are distributed or they are spread out throughout the armature periphery. So throughout the armature periphery they are distributed or spread out. So the nature of the armature winding, or rather the nature of the armature coils which are placed in the armature core, is concentrated or distributed. Which one it will be? It will be distributed winding. So what is the nature of armature winding in case of DC machine? In case of DC machine, the nature of armature winding is distributed winding. So what is the meaning of distributed winding? By distributed winding we mean that if you find the magnetic axis of the 6 coils like 1 1 dash, 2 2 dash, 3 3 dash, we will find that the magnetic axis of the 6 coils, they are not aligned in the space, rather they are separated in space, or the spatial orientation of the 6 armature coils will not be aligned, they would be separated in space. So you can just cross check here, just for the sake of clarity. I just wanted to make sure that the diagram is not getting clumsier. What I have done, I have only indicated the magnetic axis of 2 coils, 2 armature coils. What are the armature coils? Armature coil 1 1 dash and armature coil 6 6 dash here. So you see armature coil 1 1 dash, the coil side 1 is carrying cross current and coil side 1 dash is carrying dot current. So dot means what? It is leaving the board. Cross means what? Entering the board. So my right hand 4 fingers should enter along the coil side 1 because it is carrying cross current, and from behind the board these 4 fingers of the right hand should leave from coil side 1 dash which is carrying dot current. So in doing so, the thumb is giving me the magnetic axis of the coil 1 1 dash. So the magnetic axis of coil 1 1 dash is indicated by this green color. What about the coil 6 6 dash? Coil 6 6 dash, you see coil side 6 dash is having dot, whereas coil side 6 is having cross. So again, cross means what? Current is entering into the board. So my right hand 4 fingers should enter into the board along the coil side 6, because coil side 6 is carrying cross current, and from coil side 6 dash which is carrying dot current, these 4 fingers should leave the board. So you see the thumb is pointing the magnetic axis of coil 6 6 dash. So the thumb will let you know, if you apply this right hand rule, you will know that the magnetic axis of coil 6 6 dash is perpendicular to the plane containing coil 6 6 dash. So this is indicated by here. This is the magnetic axis of coil 6 6 dash. So we have indicated the magnetic axis of coil 6 6 dash. Now what is the second step we have done? We have resolved, or rather we have what should I say, we have taken the component of the MMF due to coil 11 dash along two axes, one along the horizontal axis shown by the blue line and another along the vertical axis shown by the red line. The same thing is repeated for the MMF of coil 6 dash. What is that? This green color line is indicating the magnetic axis or MMF axis for coil 6 dash. So what is done? The MMF of this coil 6 dash is resolved into two components. One horizontal, that is blue color line, another vertical, that is red color line. So now what do you see? That the horizontal component of MMF for coil 11 dash and for coil 6 dash, the horizontal component of MMF are getting cancelled out. They are cancelling each other. So only vertical component is getting added up. So in this way, if you analyze and resolve, what you have to do, I have what I have done, I have drawn here for two coils, 6 dash and 11 dash. So how many coils are remaining? Remaining are the 4 coils. So for remaining 4 coils, if you again find out the magnetic axis and resolve the magnetic axis or the MMF axis along two axes, namely horizontal axis and vertical axis, you will find that the horizontal component is getting cancelled out for all the 6 coils. On the other hand, the vertical component will get added up for all the 6 coils. So what we say, or what we conclude, that the magnetic axis of the armature winding is directed downwards like this, VA. Okay, so now we have made ourselves more or less familiar with the orientation of the magnetic flux density due to field current, that is BF, magnetic flux density due to interpole windings, that is BCP. Here CP stands for commutating poles, because interpoles are also known as commutating poles. So CP stands for commutating poles. So what is BCP? Magnetic flux density created due to interpole or the commutating poles. What about BA? BA is nothing but BA is the magnetic flux density. BA is the magnetic flux density due to the armature winding, which is directed downwards. Now what we want to now emphasize, we want to emphasize now that by commutation of the coil, let's say 11 dash, because we have taken up this example earlier, the commutation of coil 11 dash allows us to analyze that the coil side 1 will change its polarity from cross to dot, and coil side 1 dash will change its polarity from dot to cross when this coil side 11 dash moves to this side. That means once the commutation of the coil 11 dash is completed, the position occupied by coil 11 dash will be that which is now occupied by coil 6 dash. Now once we have said this, let us first try to find out that what are the induced EMF in the commutated coil CC dash. That means when coil 11 dash will undergo commutation, it will occupy the position which is indicated by coil CC dash. So when coil 11 dash is occupying the position indicated by coil CC dash, this will be the velocity vector, tangential velocity vector, because the armature is being driven in the clockwise direction. So for coil side C, the tangential velocity will be from left to right, and for coil side C dash it will be from right to left. So this is shown here separately. Now what we need to do, let us first tell us that why these conductors in slot number 1, 2, 3, 4, 6 are shown cross, and why the conductors in slot number 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, 6 dash are shown dot. This is just in accordance with your Fleming's right hand rule. Fleming's right hand rule, see, if you consider this conductor 3, so for conductor 3, what is the tangential velocity? It is rotating in clockwise direction, so the tangential velocity for conductor 3 will be upwards. So this is the tangential velocity of conductor 3. what is the direction of magnetic flux density vector BF? It is like this. So now if you apply Fleming's right hand rule, so Fleming's right hand rule says that the thumb should be along the velocity vector. So thumb is along the velocity vector. Index finger of the right hand should be along the magnetic lines of flux. So it is along the magnetic lines of flux. And the middle finger will let you know the induced EMF polarity. So middle finger is pointing into the board. Middle finger is pointing, you see, right hand thumb is along velocity vector. Right hand index finger along magnetic flux density vector. So so the middle finger is pointing into the board. So that means for conductor 3, the induced EMF polarity will be cross. So this is conductor 3 and induced EMF polarity will be cross as per Fleming's right hand rule. You can also assume that V cross B, and you can apply V cross B, you will get the same result. Now once you know the polarity of induced EMF for conductor 3, it is needless to say that all the conductors under the influence of north pole will have cross. So we have put up cross like that. So what you have to do, you first find out the induced EMF polarity for any one conductor. Let's say we have found out the induced EMF polarity for conductor 3. So for conductor 3 we have found out the induced EMF polarity. Now once you know the induced EMF polarity of conductor 3 is cross, so remaining conductors under the influence of north pole will be also cross. Now once you know the induced EMF polarity under north pole, obviously for south pole it should be reverse. So if the induced EMF polarity for conductors under north pole happens to be cross, then for south pole it should be dot, opposite of that or reverse of that. So by that way you can figure out the induced EMF polarity in the armature conductors. Okay. Otherwise you may also apply for conductor on the south pole and you can verify for yourself that it is coming as dot. On the other hand, it's not needed actually. You just find the induced EMF polarity for conductor 3, which is under the influence of north pole. It comes to be cross by Fleming's right hand rule. Then other conductors under the influence of north pole will also have cross. So for south pole it should be opposite, that is dot. Now once we have said this, now let us focus here and try to apply that same thing. But instead of doing that, you may also think over in a different way. What I want you is that you think this coil CC dash as what should I say, two conductors. Instead of thinking that this commutated coil CC dash is a coil, you think it is comprising of two conductors. One conductor is on the coil side C and you have another conductor on the coil side C dash. So for coil side C, we are assuming there is a conductor in coil side C. So for this conductor, what is the induced EMF polarity? It is in general given by BLV sin theta. Okay. So what is B? Magnetic flux density. What is V? Tangential velocity, which is already indicated in the diagram. What is L? Length of the conductor. That means this coil side CC dash is assumed to be comprising of two conductors. One conductor on coil side C, another conductor on coil side C dash. So BLV sin theta. What is theta? Theta is nothing but the angle. Theta is the angle between velocity vector V and magnetic flux density vector B. Now, what are the different magnetic field which are there? You just analyze one by one so that it is easier to communicate. So what are the different magnetic fields? One is magnetic field due to the field winding BF. So what is the orientation of BF? Like this. Velocity vector is parallel. So what is the angle between BF and V? This is V, and what about BF? BF is like this only, na? So angle between BF and V is 0 degree for this conductor and it is 180 degree for this conductor. It is 0 degree for this conductor, angle between V and BF, and it is 180 degree for this conductor, angle between BF and V. So if you put theta as 0, induced EMF is 0. If you put theta as 180 degree, so sin 180 is 0. So you see there is no induced EMF in the commutated coil CC dash due to field winding. It's clear? There is no induced EMF in the commutated coil due to field winding flux BF. Now let us find the induced EMF polarity due to armature. So what is the induced EMF polarity due to armature? First you look at here, what was the direction of magnetic flux density vector due to armature winding current. This was the armature winding current, and we have found out the direction of magnetic flux density due to armature winding. It is directed downwards. So this is my BA, which we have derived earlier. So now what is the angle between V and BA? 90 degree. Here also it is 90 degree. So you see, you will have induced EMF in the commutated coil due to armature flux density, armature winding current. Rather, I should say that the armature MMF is going to create a armature flux phi A, which will be directed along this direction, and this armature flux phi A will give rise to a induced EMF in the commutated coil CC dash. You can see it here. BA is directed vertically downwards. So I have drawn BA vertically downwards. This is the commutated coil. This is the velocity vector for coil side C. This is the velocity vector for coil side C dash. So you apply Fleming's right hand rule, or you can apply cross product of velocity vector V and magnetic flux density vector B. In either of the way, you will find that the commutated coil is having a induced EMF. So what is the polarity due to BA? You see, B cross B, so it will be cross here and it will be dot. So this is the induced EMF polarity. Okay, this is the polarity of induced EMF. Let me write it. This is the induced EMF polarity due to armature MMF. So this is the point which has to be noted, due to armature MMF. Now further, you should notice very carefully that the armature MMF or the armature winding magnetomotive force is directed vertically downwards. So we have drawn BA downwards, and we have accordingly found out the induced EMF polarity in the commutated coil C to be cross and in the commutated coil side C dash to be dot. So what do you make out of this? What we make out of this is that the flux due to armature winding current, is going to induce a EMF in the commutated coil, and this induced EMF in the commutated coil will provide a hindrance. It will provide a delay in the commutation of the coil. Why it is like that? You see here, look at the diagram. What we want, that when coil side 1 dash moves to this side of the brush, that is on the right side of the brush, when the coil 1 dash moves to the right side of the brush, then coil side 1 will occupy a position which is presently occupied by coil side 6 dash, and coil side 1 dash will occupy a position which is presently occupied by coil side 6. So coil side 1 is having which induced EMF polarity? Cross. So cross will become dot, and coil side 1 dash is having presently dot polarity. So when it moves to this side, it will become from dot to cross. But you see here in the diagram, the induced EMF polarity due to armature flux is such that it maintains the induced EMF in the coil side C to be cross, and it maintains induced EMF polarity in the coil side C dash to be dot. That means it is trying to retain the same induced EMF polarity which was there at the beginning of the commutation. It is not helping in the coil side C to become dot. Rather, it is not helping the coil side C to become dot or the coil side C dash to become cross, because when this coil side moves to this side, this will become from cross to dot. So here dot should have been induced, then only it will help in the reversal of the coil current, and this is dot. But when this coil side 1 dash moves to this side, it will become from dot to cross. So here should have been induced cross, but that is not happening due to armature flux. So what can you conclude? That the armature winding is having a magnetomotive force, and that magnetomotive force due to armature winding is directed vertically downwards in this particular case. So armature flux phi A or magnetic flux density due to armature winding current BA will be directed vertically downwards. So that is what shown here, BA downwards. So due to this armature EMF is being induced in the commutated coil, which is giving a hindrance, or which is giving obstruction in the reversal of the coil current. That means it is not allowing the cross to become dot. Rather, it is helping to retain this cross, not become dot. It is not helping the cross induced EMF to become dot. Rather, the armature flux density BA is helping the coil side 1 to retain the cross, as you can see from this induced EMF. So what has been done? We have placed an interpole. Interpoles are narrow poles which are fitted to the yoke along the interpolar region. That means the region along which air gap is maximum. Now what is the basic idea? The basic idea is that this interpole should develop a magnetomotive force, or it will develop a magnetic flux density BCP, such that EMF induced due to this interpolar flux will aid or help in the coil current to get reversed. So what is that we can do? If the interpoles are going to induce dot induced EMF in the coil side C and cross polarity induced EMF in the coil side C dash, you will find that it is helping in the commutation actually. So that has to be done. What I am saying is that the interpoles should develop a flux, or the interpoles should develop a flux density which will help in inducing a EMF in the commutated coil. And the nature of induced EMF in the commutated coil due to the interpoles should actually help, or it should aid the commutated coil to achieve the desired polarity. So in this particular case, for coil side 1, what is the desired polarity of induced EMF? It is dot, because when coil side 1 moves to this side, it will be dot. So the desired induced EMF polarity for coil side 1 is dot, because when this moves to this side, it should become dot. Likewise, for coil side 1 dash, for coil side 1 dash, what is the desired induced EMF polarity which will help in the commutation of the coil 1 dash? When 1 dash comes to this position, then it will become from dot to cross. So the desired induced EMF polarity for coil side 1 dash is cross. So what we say here, that the interpoles should induce a EMF in the commutated coil CC dash, such that here cross polarity induced EMF should be there. Where cross polarity induced EMF should be there? At the coil side C dash. And dot polarity induced EMF should be there at the coil side C. So for that to happen, obviously the direction of the interpole should be opposite to the armature. That means what? The interpole magnetic flux density should be directed in this direction. That is, this should be our BCP. So for now, if you apply Fleming's right hand rule, or you take the cross product of V, that is velocity vector, and B, you will find that for BCP you will have here cross current, you will have here cross, and you will have here dot. So this dot and cross is due to this one. However, this dot and cross is happening due to the armature flux density. Okay, so this is due to this one. So what do you see? That the EMF induced in the commutated coil by these interpoles is of such nature that it is helping the commutated coil to attain a voltage polarity which is actually needed. For example, when one moves to this side, it should be dot. So you see in coil side C, dot polarity is being induced by the interpole flux density, that is BCP. If you wish, let me make it a little clearer. Let's say this is my BCP. This is the direction of BCP. And what about BA? That is the magnetic flux density of armature. That is the direction of BA. And these are the velocity vectors. So you can find it for yourself that these are the induced MF polarity due to this flux density. Okay. So this is cross due to this one. Okay. And this is dot due to this BA. Due to BA. This is dot. So now we see that what is happening? The EMF induced in the commutated coil due to the interpole flux density BCP is of such nature that it actually helps in, it actually aids the commutated coil to attain the desired induced EMF polarity. So in this way the interpoles helps in the commutation of the coil, because it is inducing that polarity. Because when coil side 1 moves to this side, it has to acquire dot polarity, which is already being induced by BCP. In coil side C, it is dot. Likewise for coil side C dash, it is cross. So when coil side 1 dash moves to this side, it has to acquire dot polarity. So that dot polarity is being induced by the interpole flux density BCP. Now besides this, we need to keep one thing more in mind, one more point in mind. What is that? You see, when the coil is undergoing commutation, the coil current is getting reversed from IA by A to minus IA by A. So if somebody asks what is the change in current? What is the change in current? So obviously the change in current will be IA by A minus, inside bracket minus IA by A, that means it will be 2 IA by A minus of IA by A. So it will become 2 IA by A. So this is the change in current. So this is delta I. How much time is needed for the coil current? How much time is needed for the coil current to get reversed? The commutation time TC. So this is delta T. And this commutated coil is having some inductance. Okay. So what is LC? LC is nothing but the inductance of the commutated coil. So how much EMF will be induced in the commutated coil? EMF induced in the commutated coil will be given by L di dt. Di dt is replaced by delta I by delta T. Obviously delta I is your 2 IA by A, delta T is your TC, and this is your LC. So this much of induced EMF you can expect that it is being induced in the commutated coil CC dash. Here actually we are assuming that at a particular instant only one coil is undergoing commutation. But if the width of the brush is greater than the width of the commutator segment, in that case you will expect that at a particular given time more than one coil, maybe 2 or 3 coils are undergoing commutation. So in that case this LC into delta I by delta T plus mutual inductance term and the rate of change of current, that will be also added. So here I have make a simplification that the width of the brush equals to the width of the commutator segment. That means if the commutator segment is 2 cm wide, then the brush is also 2 cm wide. That means at a given time only one coil is undergoing commutation. So there is no effect due to mutual inductance of nearby coils which are undergoing commutation. So this LC into delta I by delta T, that is L di dt, will be the induced EMF in the commutated coil. Now this induced EMF in the commutated coil is known by the name of reactance voltage. It is known by the name of reactance voltage. Now this reactance voltage also plays a hindrance. It actually delays. It actually delays or it actually slows down. It actually slows down the reversal of coil current. So there is a delay in commutation. So if there is a delay in commutation, what happens? The current will take longer time to reverse. However, the time which is available for the coil current to get reversed is given by TC. What is TC? TC is nothing but width of the brush divided by peripheral velocity of the commutator. So if the peripheral velocity of the so what you see, that peripheral velocity of the commutator is a mechanical quantity. It is going to get this is a mechanical quantity, so it is remaining unaffected. WB is what? It is the width of the brush. So the commutation time TC does not changes, or rather the commutation time TC is not going to get affected due to the reactance voltage. However, due to reactance voltage which is induced in the commutated coil given by LC into delta AB delta T is definitely going to slow down, or rather it is going to decelerate or retard the reversal of coil current. So that means what? Now the coil current will take longer time to change. So that means what? You may have this kind of thing. So what you find, that earlier this much change in current was happening, IA by A change in current was happening in this much time, but now that change in current due to the delay in commutation, due to reactance voltage is taking this much time, the same change in current, isn't it? So what happens, this much portion of the coil current is not getting reversed, or it is not completed. This much reversal of the coil current is not getting completed because the contact is getting broken at this point. Or rather you can tell that this much extra time is needed for the coil current to get reversed totally. How much extra time is needed for the coil current to get reversed totally? This much extra time is needed, which is not provided because the commutation time TC depends on peripheral speed of the commutator and brush width, which is not changed. So what happens, this much current is not being able to convert, or rather this much portion of the coil current is not reversed. So this appears as spark at the trailing edge of the brush. This is appearing as spark at the trailing edge of the brush. So what is the role of these interpoles in a DC machine? The interpoles in the DC machine is actually performing two things. What are they? First, interpole MMF, or the flux density, or the interpole MMF BCP. Yeah, actually let us define FCP. So what is FCP? FCP is the interpole MMF. So we are going to use F symbol F for MMF. So what is FCP? FCP is the interpole MMF. So what interpole MMF has to do? Interpole MMF has to cancel what? The armature MMF FA. The armature MMF FA is directed downwards, whereas interpole MMF is directed upwards, like this, FCP. So this is FCP directed upwards and this is FA. So first job or the first function of the interpole winding MMF is to cancel the armature MMF FA. So FC should be at least equal to FA, isn't it? At least equal to FA. What is another thing? Besides cancelling the armature MMF FA, the interpole MMF FCP should develop a flux along the interpolar region. The interpoles should develop a flux along the interpolar region such that BCP will induce a EMF in the commutated coil, and this induced EMF in the commutated coil will cancel out the reactance voltage which is induced in the commutated coil. Because you see, you apply Lenge's law. Lenge's law says that effect will oppose the cause producing it. So what is happening? There is a rate of change of current, or rather there is a reversal of coil current. So due to this reversal of coil current, there is a change of current. So there is a change of current means what? There will be a induced EMF given by L di dt. So this induced EMF will oppose the change in current. So that means what? It will slow down or it will retard the change in current. So that's what is happening. The reactance EMF or the reactance voltage is actually delaying or retarding the change of current due to that Lenge's law. That effect will oppose the cause producing it. So what is the another function of interpole? Remember, first function of the interpole was to cancel what? The armature MMF. So you see, armature MMF was directed vertically downwards in this particular case, whereas the interpole MMF is directed vertically upwards. So FCP should cancel FA. So FCP is the MMF of the interpoles or commutating poles. So it should be at least equal to FA, that is armature MMF FA. But you see, what is armature MMF? Number of turns multiplied by armature current. So if armature current changes, then armature MMF also changes. If armature current changes, then armature MMF also changes. That is, FA will change if armature current changes. But armature current is the load current. If the loading on the DC generator or motor is going to change, the loading will change, means what? Armature current will change. So the armature MMF FA will also change. So in that case, we have to again adjust the number of turns on the interpole, because what is MMF? Number of turns into current. So what is done, you know, in order to take care of this situation, that with the loading on the DC machine, armature current will vary, and as a result armature MMF will vary, but you have to maintain the interpole MMF to be equal to armature MMF. What is done? The interpole windings and armature winding are connected in series. You can look at the diagram here. The interpole windings and the armature, they are connected in series. That means whatever is the armature current IA, that same armature current IA flows through the interpole windings. So interpole windings they carry armature current, because interpole windings are connected in series. Interpole windings are connected in series with the armature, so as to take care of the fact that if the loading changes, armature current changes, so automatically the interpole MMF also changes, because interpole windings are connected in series with the armature, so they are carrying the same current which is being carried by the armature. Okay, but as I was saying, again I am repeating that the job of the interpole is not to only cancel armature MMF FA, but another job of interpole MMF is to set up a magnetic flux along the interpolar region only, given by BCP, such that this flux density BCP will induce an EMF in the commutated coil, so as to cancel the effect of reactance EMF or reactance voltage which is induced in the commutated coil. So what should happen? That the interpole, they should develop a flux density in the air gap, such that this flux density in the air gap, of course this flux density in the air gap is directed along the interpolar region or interpolar axis, will induce an EMF in the commutated coil, and this induced EMF in the commutated coil will cancel the reactance voltage or reactance EMF. Thus what will happen? There won't be any hindrance or objection or obstruction in the reversal of the coil current, because everything is being taken care. Armature MMF is being nullified by the interpole MMF. Now you see, there has to be a thing which should be borne in mind. We are saying interpole MMF is cancelling the armature MMF. That does not mean that armature MMF is zero. What I mean to say is that if you take the combined value, or if you take the net value of interpole MMF and armature MMF, they will come as zero. But usually that is not. Usually the interpole MMF is around 1.2 to 1.3 times that of the armature MMF. So why it is 1.2 to 1.3 times the armature MMF? That extra 0.2 or 0.3 times armature MMF is there, so as to provide what? So as to provide the MMF which is needed for setting up the flux density in the air gap along the interpolar axis. That means, you see, for setting up BCP, that is magnetic flux density due to commutating poles which are set up along the interpolar region or interpolar axis, this flux density BCP will require a MMF or magnetomotive force. So that magnetomotive force has to be provided by interpoles only. So you can write this BCP divided by mu 0 into GCP is the MMF required. Because you are aware of this formula. What formula I am talking about? That H into L equals to Ni. What is Ni? Ni is MMF, nothing. What is Ni means? Ni is magnetomotive force, MMF. What is HL? H is the magnetic field intensity, H. So H can be written as what? B by mu. What is L? Length of the magnetic path. See here, look at the diagram please. If you consider the length of the magnetic path, so you are having an air gap of GCP here, you are having an air gap of GCP here, you are having another air gap of GCP here, and after that this is iron core, this is iron core, this is iron core, iron core, iron core. So we are assuming that MMF required by the iron core or iron portion is almost negligible. So whatever MMF is needed for setting up the magnetic flux, that MMF needs to overcome the reluctance of this air gap. So this air gap GCP here, this air gap GCP here, isn't it? So we are saying that this GCP is actually the magnetic, it is actually the length of the magnetic path. What is this GCP? GCP is actually the length of the magnetic path. Magnetic path of which circuit? Magnetic path of the circuit provided by this BCP. What will be the path? Please look at the board here. What is the path of BCP? BCP will take up this path. BCP will take up this path. So in this path you see this is iron, this portion is iron, this is also iron. So only how much of air gap is there? This much of air gap is there, but this much of air gap is also not there because there will be armature here. There will be armature here. So only this much of air gap. So this is GCP, this is GCP. So that's why this L will be actually GCP. So for L we have written GCP, for B we have written BCP, and since we are considering only air gap is having reluctance, no reluctance due to iron portion, so that's why we are dividing by mu 0. So what is BCP by mu 0 into GCP? This is the MMF required for setting up the magnetic flux in the air gap. So what is BCP by mu 0 into GCP? This is the MMF required for setting up the magnetic flux density BCP in the air. This is BCP by mu 0 into GCP. Okay. So now some of you might be thinking that why I am written GCP? There has to be twice because GCP here once, GCP here once. So twice should be there. But think again, how many interpoles are there? This is interpole 1, this is interpole 2. So if you count the number of interpoles, so the MMF will be double. So if you halve the MMF, then air gap will be GCP. Are you getting my point? Why I have written here GCP only? Why not 2 GCP? This 2 GCP is not written because we are encountering 2 poles, one this south pole, one this north pole. So we are written GCP because we are encountering 2 poles here. But we are computing the number of turns or MMF for each pole. What we are doing? We are calculating the MMF for each interpole. FCP is the MMF of each interpole. So that's why I have written GCP here, not twice GCP, because if you take twice GCP, then you are having 2 interpoles, 1, 2. But I am computing only MMF for 1 interpole, so that's why I am writing only GCP. Now you will find that the value of this number of turns in the interpole can be computed by this. What is FCP? FCP is nothing but number of turns in interpole NCP into IA. As said that interpole windings and armature are connected in series, interpole windings and armature are connected in series, so current will be same. What is armature MMF FA? What is armature MMF FA? You see, it's easy. How you can find? Let's say the total number of armature conductors is Z. So if the total number of armature conductors is Z, in that case the number of conductors under each pole will be Z by P. So that is what Z by P is, the number of conductors under each pole. Now what is the current carried by each conductor? It is IA by A. So Z by P is the number of conductors under each pole multiplied by current carried by each conductor, that is IA by A, will give you what? Ampere conductors. But you want to find MMF. So that means what? If you want to find the number of turns, you have to divide the number of conductors by 2. The moment we divide the number of conductors by 2, we get number of turns. So you divide by number of what you do, you divide by 2 in order to get the number of turns. So that's what I am saying, that total number of conductors is Z. So conductors under each pole is Z by P. Each conductor is carrying current IA by A. So ampere conductors under each pole is IA by A into Z by P. But if you want to find the equivalent number of turns, you have to divide by 2. So that's you get in this way. Let me tell once more. Total number of armature conductors is Z. So total number of poles is P. So Z by P is what? Number of conductors under each pole. Each conductor is carrying current IA by A. So ampere conductors under each pole is Z by P into IA by A. Now you divide by 2, you get equivalent number of turns. So Z by 2P into IA by A is the armature MMF FA, and this is the MMF required for setting up the magnetic flux density BCP in the air gap. Okay. So this is it. Just for a sort of revision, I would like to tell what is the polarity of interpole in case of generator. Polarity of interpole in case of generator, polarity of interpole in case of generator will be same as that of the main pole ahead of it in the direction of rotation. So you are rotating, or rather you are moving in the direction of rotation in the clockwise direction. So what is the main pole ahead of this interpole? What is the main pole ahead of this interpole? South pole. So it will be south pole. So that's what I am saying, that in case of generating action, the polarity of the interpole is same as that of the main pole ahead of it in the direction of rotation. Obviously for motor it will be reverse. Okay. Now what about the number of interpoles? The number of interpoles should be equal to number of main poles. Here number of main poles is what? 2. So the number of interpoles is also 2. So number of interpoles equals to number of main field poles. However, for small machine where the rating is say less than 4 kilowatt or 3 kilowatt, the number of interpoles can be half that of the main poles. And in case of very small DC machine, interpoles may not be used because their resistance commutation is sufficient for improving the commutation. Okay. Okay, let it be up to this. Thank you.